Welcome back, everyone. Today we're diving deep into one of the most fundamental concepts in chemistry, atomic radius. Whether you're an undergraduate student prepping for exams or just a curious mind, this video will help you master atomic radius and its trends across the periodic table. Let's get started. Let's start with the basics. Atomic radius is the size of an atom, typically measured as the distance from the nucleus to the outermost electron. But here's the catch. It's not fixed. Atoms don't have rigid boundaries, so scientists often calculate an average radius based on models like covalent, ionic, or metallic bonding. One of the most important factors is nuclear charge, which is determined by the number of protons in the nucleus. More protons mean a stronger positive charge, which pulls negatively charged electrons closer to the nucleus. This stronger pull shrinks the atomic radius, especially across a period where the number of protons increases while the number of electron shells stays the same. This is why atoms get smaller as you move from left to right on the periodic table. While the nuclear charge pulls electrons inward, inner electrons create something called the shielding effect. These inner electrons reduce the effective nuclear charge felt by the outermost electrons, allowing them to stay further away from the nucleus. The shielding effect becomes more significant as you move down a group. This is because new electron shells are added, increasing the distance between the nucleus and the outermost electrons. The result? A larger atomic radius. Now, let's talk about energy levels. Electrons occupy regions called energy levels or shells, and each level is further from the nucleus than the last. As you add more energy levels, like stacking floors in a building, the atomic radius grows larger. Valence electrons, which are the outermost electrons, are especially affected by the shielding effect and the energy levels they occupy. These factors work together to make atoms larger as you move down a group in the periodic table. Let's talk about trends in the periodic table. When you move down a group, the atomic radius increases. Why? Because with each new row, a new electron shell is added, placing the outermost electrons farther from the nucleus. Here, the shielding effect plays a dominant role. The increased shielding from inner electrons outweighs the effect of a greater nuclear charge, leading to larger atomic radii. But what about transition metals? These elements are special because they have inner d electrons that contribute to shielding. However, d electrons are not as effective at shielding as s or p electrons. As a result, the atomic radii of transition metals remain relatively similar across a period, breaking the usual trend of decreasing atomic radius. There's more than one way to define atomic radius, depending on the type of bond or environment the atom is in. Let's break it down. Covalent radius. This is half the distance between two nuclei in a covalent bond. It's a practical way to measure atoms in molecules. Ionic radius. This applies to ions. Cations, or positively charged ions, are smaller than their parent atoms because they lose an electron shell. Anions, negatively charged ions, are larger due to increased electron-electron repulsion. Metallic radius. This is the size of atoms in a metallic lattice, measured as half the distance between nuclei of adjacent atoms. Understanding atomic radius is crucial for predicting how elements behave. For example, smaller atoms like fluorine have stronger electron-nucleus attraction, making them highly reactive, while larger atoms like cesium are more likely to lose electrons. This knowledge plays a vital role in fields like nanotechnology, materials science, and drug discovery, helping scientists design new molecules and materials with desired properties. And that's a wrap on atomic radius. We've covered nuclear charge, shielding, energy levels, periodic trends, and more. Thanks for watching.